So they're not just the most basic, but sometimes, as you saw in the example of, for example, f of x equals 1/2 of x, is that points nearby may converge to this fixed point, right? So fixed points, in the case of the identity map, every point is fixed and every point does its own thing. But in other cases, the fixed points act as a kind of organizing hub for nearby orbits, right? And these have a special name and a special importance, so I want to spend a little bit of time talking about these, attracting and repelling fixed points. So, so the definition is that P x is an attracting fixed point. If there exists a neighborhood U such that x n converges to P for all x 0 U. Okay, so maybe this is quite intuitively quite obvious. So this is P, this is the neighborhood U, okay? And I'm assuming that every point in this neighborhood converges to P. So we define what's called the basin of attraction. P is just the set of points Z in X such that when you set X in X such that X and converges to P. So this, by definition, this basin contains a neighborhood of P. It may be big, it may even be the whole space. We say that P is globally attracting. If P of P is equal to the whole space X. So this situation is in some sense the simplest possible from the point of view of our goal. We said, right, the goal is to describe all the orbits of all the points, right? And if the orbit converges to a fixed point, in some sense you have described it. So part of the discussion we have is what exactly do we mean by describing the orbit, right? In theory, you would like to say exactly what the points of the orbit is, but that is usually unrealistic. But if you say, well, I don't know exactly what the exact points are, but I know it converges to P, so that means that after some time it will be in a small neighborhood of P. You've described in some sense at least the asymptotic behavior of this orbit. And in the examples above, in the linear map when A is less than 1, well, then we see the example where everything converges to the fixed point. Can you think of a general class of maps which have globally attracting fixed points?
Contractionals?
Yes, it's a very well-known, well, by the contraction mapping theorem. So you know that if X is a complete metric space, and F X to X is a contraction. Okay, this means that the distance between f of x and f of y is less than lambda times the distance between x and y for some lambda strictly between 0 and 1 and for all x, y, and x. Okay, then there exists unique P fixed point which is globally attractive. So I'm sure you've all seen the contraction mapping theory before. It's a very simple theorem, but it is really has a lot of applications. It is often stated just as a fixed point theorem. as a theorem that proves the existence of a fixed point, but the proof shows that the proof uses the fact that everything is attracting to that fixed point. Okay? So in fact, the main proposition in the proof for us will have also independent interest. So I want to state this proposition. Proposition is that if f x to x is continuous, and you have some orbit that converges to some point P, okay, then this implies that P is a fixed point. So this is a little bit kind of going the other way around, right? What I'm saying is I have a continuous map. I know that you have some orbit converging to some point, which I don't know whether it's continuous, whether it's a fixed point, and I'm saying that this implies that it's a fixed point. Okay, I've left this as an exercise. It's very simple actually. It's just using for the continuity, the limit of the image of a sequence is equal to the image of the limit of the sequence, right? And you immediately get this. But once you have this, then the proof of the contraction mapping is almost trivial, right? Because you use the contraction to show that every orbit is a Cauchy sequence, right? So the key way in which this is used is to show that because you have a contraction, every orbit is a Cauchy sequence, and then by completeness it means that it converges, and then we use this proposition to show that it converges to a fixed point. And it's trivial, right? So this proposition also has a very simple proof, but it's kind of quite important. And so this shows that every point converges to a fixed point, and of course this fixed point must be unique, because if you have two fixed points, they will not satisfy this, right? Because if you have two fixed points, the distance stays the same, it cannot be less than 1, so it's a unique fixed point. So the contraction mapping theorem has a very simple proof like this. This will be used in other situations that we're interested in. And okay, in the notes I gave a few examples based on the ones we had before, but I don't think we need to spend too much time on them. Let me say that what about repelling fixed points? How do we define a fixed point that is, it's a little bit more tricky to define what we mean by repelling. What is a repelling fixed point? So if we have the map f of x equals 2x, right, on the real line, then you can see that 0 is a fixed point, right? And points move away from 0, right? So intuitively, 0 is a repelling fixed point. It's not an attracting fixed point. If you take 1/2 of x here, then all the points are moving towards 0. If you take 2, they're moving away. So in this particular case, f is invertible map. So I'll not emphasize this again, but in a lot of the definitions and the results, there's a big difference between invertible maps and non-invertible maps, simply in terms of how you need to make the definitions and how you need to prove things. So for invertible maps, a lot of things are much easier. And in this case, invertible map is, the inverse exists. This is invertible, right? F minus 1 of x is equal to 1/2 of x. So in the invertible case, in some sense you could say, well, you could say that 0 is an attracting fixed point for the inverse. Right? So for the inverse, it's like going in backward time. So maybe I did not emphasize that when I talked about define the orbits. Sorry, in parentheses that I forgot to say. If f is invertible, we can talk about the backward orbit of a point, right? So I define the forward orbit. That's why I put the plus here like this. If f is invertible, we can define x minus n simply to be f minus n of of x naught. If f is invertible, then f minus 1 is just another map from x to x, and we can just go backwards exactly the same way in which we're going forwards, right? So in that case, we define the full orbit over point x0 is just equal to xn equals minus infinity to infinity. This is the full orbit. When x is not invertible, we will see in 10 minutes, I will talk about what we can do. We can still talk in some sense about the backward orbit to some extent. But so the invertible case has this symmetry, which allows us to make some definitions like this. So the repelling fixed point is just attracting for the inverse. But if it's not invertible, for example, in the map 10x mod 1, right, we just saw the fixed points. If you take the point 0.333 in the 10x mod 1, that point is not attracted. Right? There's no neighborhood of points that converge to that. Instead, it is repelling. So how do we define it in the general case? Well, we just define it really in a very hands-on way. We say that P is a repelling fixed point. If there exists a neighborhood U such that for all x0 in U, there exists some n greater than 1 such that xn is not in U. It can come back, yes, because you cannot, in the case of repelling, if you take, this is a local property to be repelling, yes. So you might even have a point that comes back exactly on the fixed point itself, right? If you take 0.333, in 10x mod 1, then more or less by that property that I tell you, if you take 0.3, obviously every point will eventually escape some neighborhood of this, but you might have a point that has 0.333 and then lots of other digits and then finish in 3, right? So that is actually eventually going to come back and stay, land on the fixed point and stay in that forever. So this is a definition. In the non-invertible case, this is a perfect example of how the non-invertible case is quite a bit more subtle than the invertible case, and you need to adapt some of the concepts and definitions to this, and we will see this in many situations.
What if all the points go back to the fixed point?
Excuse me?
What if all the points in the neighborhood go back to the fixed point? Is it going to be both attractive?
I'm not sure that can happen, but I can't think of if there's a whole neighborhood that escapes,
Yeah.
but then land again on the fixed point.
Something not continuous.
Not continuous or not or singular in some sense. Yes, if it's any kind of smoothness, that cannot
It's
happen.
going to be both attractive and repelling.
Maybe. Let me think if that can happen. Well, it can only happen if you have some kind of degenerate situation, like it's constant. So, yes, you can do that. You can define that, right? You can have a map that looks like that in the neighborhood, right? But then at some point it's just constant, equal to 1/3 everywhere else, and so they all come back. But it's a very degenerate situation. Yeah, you're right. You can construct all sorts of counterexamples to all kinds of things. Thank you. That's a good observation. Attracting and repelling are really words that we use to help to describe things, right? They're not rigid definitions. They're words that we use to help us understand what are the possibilities that can occur. And in particular, they lead us naturally to the question of what happens if an orbit does not converge, right? So here you have a sequence, and if it converges, it must converge to a fixed point, to an attracting fixed point, or to a fixed point anyway. And so in many cases it may not converge. Right? So we define this very important concept is we define what we call the omega limit set of a point x0 is simply the set of limit points of the forward orbit of x0. So if this orbit converges to a point, then this will consist of just that point. But in general, we shall see examples now, it may have lots of limit points. If f is invertible, then we can also define what we call the alpha limit set, which is just the set x of limit points for the backward orbit. Okay, let me just put this. Backward orbit is just the orbit for the inverse. Okay? And notice that this is the limit point, so a more kind of usable definition, well, just a trivial, more precisely formulation of this is just that means there exists a subsequence nj infinity such that nj this is, so let me call this z, otherwise it can create some confusion. Z such that x converges to z, right? So the limit points is just all the points for which some subsequence converges to this point. This. Okay, and the same for the alpha limit. So, what are the limit points in the examples that we have done? So for I will leave the affine maps of the real line. You can easily see basically either. So the omega limit does not always exist, right? Is not always non-empty. For example, if you take the translation on the real line, the points just go to infinity, and so they don't have any limit points. So it's not always defined. If x is compact, then it's always non-empty. Right? So proposition, if x is compact, this implies that omega x naught is not empty, because every sequence has a converging subsequence. Right? So the omega limit set captures to some extent the topological asymptotic behavior of the orbit. Right? So this is really the best we can do in many cases, instead of describing exactly the points of the orbit, at least what are the limit points, right? If a point belongs to the omega limit set dynamically, this means that the orbit comes infinitely many times close to it, right? The intuitive meaning of this limit set, so you take a point x naught, and suppose you take a point x z in the limit set, okay? What this means is that there's a subsequence of the orbit converging to z, okay? In particular, what that means is that any neighborhood of z will have infinitely many points of the orbit, any neighborhood. Okay? So the purpose of the omega limit set is to capture that. On the other hand, if a point is not in the omega limit set, then there is no subsequence converging, which means that there is a sufficiently small neighborhood that does not contain any points of the orbit. Right? So if a point is not in the omega limit set, then it is separated from the orbit. Okay? If it's in the omega limit set, then it cannot escape the orbit somehow. Okay? This is the intuitive meaning. So from a topological point of view, it tells you where the orbit comes back infinitely many times. So what are the omega limit sets in this case? So for the map, for the affine map on the real line, I will let you think about that. It's fairly simple. It's basically always either a fixed point or empty. But what about for the circle rotations? So let's go back to the circle rotations. So we know that when maybe I should say, okay, so it's quite easy to see that if x is a fixed point, its omega limit is also the same fixed point, right? Because the sequence is a constant sequence, so the only limit points are the point itself. If x naught is a periodic point, also the omega limit set is just a periodic point itself, because it's just the omega limit. So in the fixed and periodic point cases, we've not done more than just describe those fixed and periodic points anymore. So when B is rational, then every point is periodic. Okay? So the theorem which I will leave as an exercise is that if B is irrational, then the omega limit set is the whole circle. So every orbit is actually dense in the circle. So take a point x naught, you iterate it by b. It can never come back exactly on itself, otherwise it would be periodic and b would be rational, right? But what is non-trivial is that it actually comes close, arbitrarily close to every single point in the circle. Okay? Again, I will leave this as an exercise, although this is not trivial. There's a few technical things. If you need some help, we can go through the proof, or you can easily find it. I haven't put the proof in the book, but okay, let me say just the main steps of the proof are the following: is that the step one is that if you take any epsilon, if you cover the circle with small epsilon covers, you can always find 2 points of the orbit that are within epsilon of each other, right? So there exists xn and xm, both of which are in there. That's easy, that's just the pigeonhole principle, right? So the first step is to show that this orbit must be infinite, right? So why must it be infinite, the orbit? So, sorry, the orbit is infinite. Why should it be infinite? Because if it was finite,
Periodic point.
it would be periodic or pre-periodic, we just said, right? This is a general fact. If the orbit is finite, it must be periodic or pre-periodic. And we know it cannot be periodic or pre-periodic, otherwise B would be rational. Right? So the first observation is that the orbit is infinite. Okay? And from that, it follows that if you cover the circle with arcs of size epsilon for any epsilon, there must be some arc that contains 2 points, in fact, infinitely many points, right? Because it's you're putting infinite number of points on the circle, so you have a finite number of arcs, so you must have 2, right? And so if you take these 2 points here, then one is the image of the other under some iterate, right? So xn is equal to fn of x0, xn is equal to fn of x0, which means that xn minus xm is equal to f n minus n. So it means that, what it means is that f n minus n of xm is equal to xn. Right? Because you take this point xm, if you go backwards by n, f minus n, you go back to x0, then you go forward by n again and you end up in xn. Right? So that means that you have this here, and this means that f minus m is a rotation by an angle that is less than epsilon. Right? So you can now define a new map that is Fn minus m, and this map has a rotation minus less than epsilon, so if you start from this point here, or if you start from here, it will cover the circle, it will be epsilon dense in the circle, right? And all the points, so if you now take f, k, n minus m, like 0, right? So you use f n minus m as your new map, and you apply it to x0, you will be shifting by less than epsilon each time, okay? So clearly this set will be epsilon dense. Okay, since you can do that for arbitrary epsilon, then it means that the orbit is dense. Because all the points in this orbit, there are also points along the orbit of F, obviously. Okay, this is just a short sketch of the proof. But I encourage you to do it. I did not mean to write it to say it so that you have understood it, okay? Just to give you some clues to do it. But it's a very interesting result. Circle rotations are a huge field of research. There's actually a lot more things to say. The fact that every orbit is dense is remarkable because it's true for every irrational B, right? But it turns out that there's lots of other things that can be said, very fine things, some of which depend, maybe Massimiliano works in some things that have to do with this. Yeah, there's a KM theory called Mogolov-Arnold-Moser theories, one of the theories in dynamical systems that studies perturbations of invariant tori, and these numbers come very much into it. They're called rotation numbers in more general situations. So this is just the simplest setting, but it's worth spending a little bit of time doing this exercise. So what about for the 10x mod 1 case? Do we have dense orbits? Do we have any dense orbits there? Or what is the omega limit set of different orbits? So f of x equals 10x mod 1. So let's take a point that is not rational. Okay, now it's a point. Now here, the interesting thing about this is that every point has the same behavior. The remarkable fact about circle rotations is that depending on the B, either every point is periodic or every point is dense. Every orbit is dense. Whereas here we've already seen that we have a dense set of periodic points, or pre-periodic points, but these are just the rational points, right? So the irrational points cannot be periodic or pre-periodic. So what happens? Let's choose an initial condition here that is not rational. What can we say about the omega limit set of this point? Can it be dense? How can it be dense? Give me an example of a point with a dense orbit. What does the decimal expansion look like? Let's take it step by step. How do we make sure that the fixed point P equals 0.7 belongs to the omega limit set of x naught? Suppose I just want to know that. I said, okay, so a trivial situation, so if the decimal expansion of x naught finishes with all sevens, then at some point it will land on this, but this makes it a pre-periodic point, prefixed point, right? So what if it's not prefixed, but we want it to come arbitrarily close to this? How do I guarantee that it's in an epsilon, at some point it will be in an epsilon neighborhood?
We must have an arbitrarily longer list of 7.
Exactly, right? Very easy. So it needs to have an arbitrarily long list of sevens. For example, I could say 7, 1, 7, 7, 1, 7, 7, 7, 1, and so on. 4 sevens. Okay? and then I say, okay, if I want to be within epsilon, if I take very small epsilon, all the points are within epsilon, they have 1,000,007s. If you have 1,000,007, if you start with 1,000,007s, like 0.7, 1,000,007s, it doesn't matter what happens afterwards, you're within this epsilon neighborhood. Okay? So then, if I look at this sequence, I just wait long enough, and it's remember that when you iterate, all you're doing is shifting this, right? This is why I spent some time explaining how the orbit of this thing works, right? You're just shifting the sequence. So after this, you get 0.177, then 0.77, and so on. So you keep shifting. At some point, you get where it goes 0 point, and then you got 1,000,007s, right? So if I have arbitrarily long sequences of sevens, it means there is a subsequence of the orbit. So I choose the subsequence by taking the points at which I will start the sequence, right? The subsequence will be from here, and from here, and from here, where the decimal expansion starts with very large sevens, and this subsequence is converging to this fixed point. Suppose I take another fixed point, 0.5, and now I want both of these points to be in the omega limit. And I just need to have arbitrarily long sequence of 5s and of 7s. Right? This is easy. I just alternate them, right? 5, 5, 7, 7, 5, 5, 5, 7, 7, 7. So how do I get a point that approximates every single point in orbit?
Like the list of all numbers.
Exactly, right? So it's easy. I just have to contain, so 0, 1, 2, up to 9, and then 0, 0, 0, 1, 0, 2, up to 99, and then I start 0, 0, 0, 0, 0, 1, up to 999. So I concatenate all the finite blocks because there's a countable number, right? For each, if I look at all the sets of 3 digits, there's a finite number, and I put all the sets of 3 digits in a row. Then I take all the sets of 4 digits, all the combinations, and I put them in a row, and I concatenate them, and then I will have every possible finite block will occur in the decimal expansion. Right? And this means that if I take arbitrary point here, z, which has a certain whatever decimal expansion, and I want to be within epsilon, so I need to have the same 1,000 or 1,000,000 digits here. Eventually I find exactly that sequence of 1,000,000 digits because every single finite combination of digits is in my decimal expansion. So you can play around. This map is nice because there's so many, you can really explicitly play around with all kinds of things. So how many points are there with dense orbits? Here we've constructed 1, but how many can we construct? Exactly, we can permute all the blocks. Okay, that's one way in which we get different points. Really different points. Like, of course, we can also take points along the orbit of this, and they will also have all finite blocks, they will also be dense. But we can permute them. Not only we can permute them, we can also add all the finite blocks in between these blocks. You can do lots of stuff, right? And we're going to play around with this. So practice a little bit. You can take, as long as it's got all finite blocks, it can contain lots of other stuff as well, and it's still going to be dense. Okay, that's interesting things. How do we construct one that is not dense? So for example, suppose I take this into 0.5, 0.6. Let me take just the interval, half closed and half open. And how about I want a point that does not intersect that interval? I want to guarantee that it does not intersect that interval. Sorry?
No 5s.
Exactly, very easy. Right, very easy, no 5s. So of course, all you need to make sure is that there's a finite block that doesn't occur. Right? So if the density means it must have all finite blocks, if you remove a finite block, so you make sure that you never have 5, 3. You never have the block 5, 3, then it means that if you here you take between 0.53 and 0.54, you're never going to enter that interval because you're never going to have your decimal is 0.53. Okay? What is it going to look like, the set of points that doesn't have 5, 3 in it? Do you have some idea? What's the
We've
topology?
already seen,
Sorry?
we have already seen one, like the one with 1 and 7.
Yes, but what if, I mean the whole set of points.
Oh, okay.
What is the set of points?
Like the Cantor set.
It's a Cantor set, it's exactly a Cantor set. Right? Because you need to think about it a little bit. But at every level it's got gaps, right? Because you take any open interval and every open interval has some points that has every block in it. So you remove that block, so you're removing a countable number of open intervals there. Okay. Okay, so this is okay, so there's one more subtle definition that I want to talk about, which will be very important. And then tomorrow we'll move on to the ergodic part, right? So here I'm setting the stage. Tomorrow we're going to revisit all these cases, talk about the sequence of measures, of the Dirac measures, right? So tomorrow we're going to look at all these cases. So if you have a dense orbit, if you don't have a dense orbit, what happens to this probability measure that you get, right? Because that's where it gets fun. Yeah. So the last definition, which is important that I want to introduce, is the concept of invariant sets. These play a very important role. So we say that lambda in X is invariant if F is lambda equals lambda. Sometimes we can, okay, yes. Okay, so examples of invariant set, we have examples, obvious. Right, a fixed point, periodic point. What about the orbit? Is this invariant?
Yes.
It should be invariant, right? But think about it carefully. So this orbit is formed by the points x0, x1, x2, and so on, right? And what is the image of this orbit? What points belong to this?
X1, X2.
Right. We're missing a point. Missing a point. This is a perfect example of what I said about there being a lot of little subtleties that you have to be careful of here. So what is the smallest invariant set that contains the orbit of a point? How do we, so can we, we have a point, we have this orbit. Clearly, if we want an invariant set, it needs to contain all the forward images, right? Because they're all the forward images. Yes. What points do we need to add?
If F is invertible, then the log is
Exactly. So if F is invertible, then the full orbit is invariant. Okay, because the full orbit just goes from, it contains all the points, also backward, so it is invariant. What if X is not invertible? What if F is not invertible?
You have to take the intersections of the orbits.
Excuse me?
You have to take the intersections of the orbits of x0, x1, x2, x3.
The intersection of the orbits, but the forward orbits all coincide, right? The forward orbit of x0, of x1, just the same as the forward orbit of x0, except for x0.
Yeah.
So the intersection would be empty, right? None of these points, but you're going in the right direction. This is the right kind of conjecture that we want, right?
The pre-made,
Sorry?
the pre-made.
The pre-images. Okay, so I promised that we would talk about something. So what is the pre-image? So even if f is not invertible, we define what we call f minus 1 of x naught to be equal, by definition, the set of points z such that fn of z is equal to x naught. Sorry, f minus n. Sorry, f minus n of z, yes.
But could be empty.
So if f is if x naught is in the range of the function, it's never empty, right? Because there's always points that map to it. Yes, if it's not surjective and x naught is out, it's not. But the question is whether this is a unique point or whether it's many points, right? Is one of the key points. So if f is invertible, this corresponds exactly just to the backward orbit of the point. But in general, it's many points. So let's again look at our favorite example, 10x mod 1. What are the pre-images of the fixed point 0.3333? Right? Example, for our favorite example, 10x mod 1. So what is f minus 1 of 0.3? What are the pre-images of the fixed point 1/3? Exactly. How many pre-images does it have? It has exactly 10 pre-images, right? So this is just a set of 0.j3, right? Where j can be anything between 0 and 9. This is just the first pre-image. Is that clear? Yeah, the decimal expansion. So you can see that you have lots of pre-images, right? So if you take f to the minus 10, then as long as after n decimal places you have all threes, that will be the nth pre-image. Okay? So we can define I think I defined the whole set of pre-images. Anyway, what is if you take the union of all these pre-images in this example here, you can see that you get a lot of points. In fact, you get a dense subset. So in fact, even though 0.3 is a fixed point, right? If the map was invertible, the pre-image would be also just a fixed point. But in this case, the set of all pre-images of all for all n is dense, right? Because you can have a million, you can approximate every point, right? Because you can have a million digits and then you finish all in threes. So in fact, the pre-image of every periodic point and every fixed point is dense in the whole interval. So if we do this, do we get an invariant set? If we take all the pre-images, let's see. So let's take the orbit of x naught. Wait, I think I introduced a notation for this to make it easier. Let me call the backward orbit with a little hat on, in the case that is not invertible, will be the union of x0. So this is the union of all the pre-images. Okay? So what if we now take the full image, the union of all the pre-images? Is this invariant?
Subjective.
It is surjective, it is surjective. Yes, so it's invariant. Every point in here, the image of every point in here also belongs here. Right? Because of course, if you take a point that's a pre-image of order n, its image will be a pre-image of order n minus 1. Right? So the union of all pre-images has this. Okay, so this is invariant. So this is the smallest invariant set that contains the point x naught. Right? So if x naught is a, well, unless x naught is a fixed point, in which case you don't need to take the pre-images actually. But if x naught is not a fixed or periodic point, then you need to take the full orbit and the backward orbit. So just to finish off here, this, yes.
Can we just take a particular choice of the pre-image?
You're right, I'm sorry. You're right. So we can take a particular choice. So, so we could choose a branch of pre-images. So we could choose a sequence. You're right, sorry. This is invariant, but it's not the smallest point. So we can also choose the sequence x minus n equals 0 to infinity with f of x minus n equals x minus n minus 1. Right? This is a particular branch of pre-images. Yes. So when you take, you choose one of these pre-images, and then that point has lots of pre-images, you choose one, and at this stage you choose one and you get a particular branch. So you're right, that's the smallest invariant set, yes. So this is one branch. One branch. Okay. So the final definition I want to make is that we can go one step further in this notion of invariance, and we can define lambda is fully invariant if f to the minus 1 of lambda equals lambda. So what is the difference between fully invariant and invariant?
That, for example, the particular choice wouldn't work on
Exactly, exactly. So you can easily check, this is all in the notes and the exercise, right? I will send them, I will make them available to you. It's easy to see that, well, first of all, if it's invertible, they're equivalent. They're exactly the same. If it's not invertible, they're not equivalent. And the reason why I'm spending some time insisting is because this definition will be really important, especially in the ergodic theory part. This is very relevant, this definition of invariance. And this is a stronger definition of invariance. So in the general case, if you have this, it's easy to check that it implies the other definition of invariance. But the other way around is not true, right? For example, this case, or even this case, does not satisfy this. Why does it not satisfy this?
Which one? Sorry.
If you take a forward orbit of a point, plus all its pre-images, it still does not satisfy this.
Because, for example, say x1 is the image of something that is not x0.
Exactly, right? We're missing the pre-images of the images. So what we've done here is we've taken the forward orbit, and then we've taken all the pre-images of this point x0. Right? But now this forward orbit contains a point x1. Right? x0 is one of the pre-images of x1, but x1 might have some other pre-images that are not contained in here. Right? So here you really need, this is again a case where this seems like a very simple definition, but it's quite subtle. So to really define a full invariant set, you just need to take the union of this set for the full orbit, right? So for each point along the forward orbit, you need to take the union of all the pre-images of that point. And that is a fully invariant set. And the reason why these fully invariant sets are important is because it's quite easy to check that the complement of a fully invariant set is also fully invariant, right? So when you have a set like this, it's really a fundamental block in the dynamical system because it splits the dynamical system into lambda and the complement of lambda. And every point in lambda, all its forward and backward images, all the points which are in any way related to the orbit of lambda, they stay in lambda. And the same for the complement of lambda. Okay? This would be an important point. So that's why fully invariant is somehow more fundamental than any of the other concepts of invariant. Okay, you can relax this. Sometimes the word invariant is used to mean just that the image is contained inside the set. So invariance is used in many different ways. Okay, so sometimes you say invariant graph of lambda is contained in lambda, in which case we wouldn't have all these problems that we had. But with this definition, there's a big difference between contained and equal, and I just wanted to emphasize that. Okay, so I think we've covered pretty much all the fundamental concepts, topological concepts of the description of the orbits and so on. So we're in a good position to start introducing already because we only have 10 lectures, so I didn't want to spend too much time on this. But if you want, we can go through them. You know, if you have some difficulties, what we will do tomorrow is we will revisit these concepts and look at what happens with the measures in all these cases. So if you do have time to look through this, what is the best way for me to get the notes to you to communicate? Or what should I just send them to Massimiliano? Should I send you a link, or should we have some kind of group? Have some suggestions? Sorry? I'll send you a link. I'll send Massimiliano a link and he can send it.
I don't know if there is a web page of the course. Maybe.
That's a good idea, yeah. Okay, I will figure out what we can have. As I would like to have some system where you can also ask questions. I will think about that. But I will try to get you the link already today, maybe. Yeah, I can send it to you today, so you have it. And yeah. Okay. Thank you very much. And see you tomorrow.